Hey there, welcome to episode 99 of the Quaggling Sand audio program. I am your host, Dan Hugo. We are recording this at 1:09 p.m. Pacific Time on Wednesday, October 1st, 2025. Today, my upstairs neighbor is in rare form, so if you hear some banging, knocking, bodies being thrown to a floor, power tools, who knows? I'm kind of hoping he's moving. It is the beginning of the month. So I'll apologize for that now if I'm unable to remove such things. Today's episode is about labs. Labs. Oh, that's right. Like when you're in a laboratory and you're mixing chemicals or taking measurements, that sort of thing. If you're not familiar with the Quaggling Sand audio program, it's basically a monologue. It's audio essays, it's stories, tales, recollections, maybe something interesting, maybe not. Actual factual tales from which to draw whatever you might. If you're not familiar with the term quaggling sand, it is a technical term. It is a reference to the return of circulation, the sensation that occurs when circulation returns to maybe a hand or a foot or another part of your body that's been compressed or otherwise has had its circulation blocked. So as circulation returns, I think you probably know it better as pins and needles, but it is indeed quaggling sand, a term I coined a very long time ago, but it is the actual term to use. There you go. Yeah, depending on where you found this audio program, you hopefully will be able to locate the episode description. I'm pretty sure it appears wherever I've seen. We are now available on more places. We'll get to that in a moment. The episode description contains the show notes, which includes a summary, which is 2 sentences, which I'll read. And then the links, I have trimmed down the links on my various weekly programs. They will rely on those who are actually interested to follow through on the profile page, linking everything. If there are episode links that are relevant or interesting, those will still appear. Today there are no such links. So we're left with the usual 2 down from 4, what I typically call the shameless self-promotion links. So let's begin. Summary of today's episode. Who among us doesn't remember high school chemistry class back in the day? Do they still have that? Oh, okay, 3 sentences. I always liked lab classes for chemistry, physics, biology, and later engineering, and more of those pure sciences. I don't know if there are any other pure sciences, but we'll leave it there. The links for today's episode, the quagglingsand.com website will be the place to go for links to other sources to locate this audio program, etc. There needs to be more content there. I'll just leave that there. Today is the beginning of Oktoberfest, by the way. It's a month-long open source call for new contributors and so on. So as I think I mentioned in the Monday Buy Me an Update, since there will be some website stuff to do for that also, I need to clump all of this together in my to-do list, reordering. So enough of the excuses. The profile page linking everything remains at buymeacoffee.com/DanHugo. That's been there for about 5 years now, maybe. It's a freeform profile page. I have links to all of my audio programs, all of their homepages, all of their YouTube links. You can listen to Quaggling Sand on YouTube. The podcast, the video version of the podcast is a single frame. The cover art, it's auto-generated by YouTube. But there's a podcast tab with a podcast playlist. You can visit youtube.com/@quagglingsand. But there's a link to that in both places, quagglingsand.com and buymeacoffee.com/DanHugo. You don't need to buy anything. You don't need to spend any money at buymeacoffee.com/DanHugo, but you will find the first posting of the Buy Me an Update program there. It then gets posted to other places, maybe an hour or 2 later. And then there are various affiliate links on that profile page for things I actually use. So if you would like to support my efforts, you can do that without spending any actual additional money. If you find any of those things interesting and purchase or otherwise subscribe to those things. Affiliate links don't cost you anything extra. That's what they tell me. On that note, let us begin. First with the early days. I cannot for the life of me remember the cardboard drawer module box name that we had in the classroom for each of my elementary school years. They were the most basic of science experiments. They were like plastic bags full of parts and some instructions, and you got what you got. I mean, demonstrating the simplest of scientific concepts, but it was hands-on and practical. I want to say when I was in Sunnyvale and I was pursuing the parcel tax increase that would fund science education. I learned at that time that there was about $2.75 spent on classroom equipment and curriculum materials in general for teaching science, or STEM, really. So, but math labs are pretty much chalk. But anyway, so these were not super expensive. They probably were overpriced, but they were not overly intricate. So that was the beginning. It was just enough to call it some sort of a learning exercise, but barely. I think growing a potato with toothpicks in a jar of water. I wrote "and a jar of water," but it could be both, and in. That was pretty much the leading edge at that time. So, but good for us. And this, by the way, was typically through the 6th grade. If there was a junior high school or a equivalent, that's usually where you get into some more hands-on stuff. So in my case, I switched schools. I had some. I don't mean it's not a competition, but I had some really good. I'll just say good teachers in junior high school, a different school district. Our advanced biology teacher was a butcher at Smitty's, which was a grocery store, like more of a grocery plus, kind of like a Target. He worked at Smitty's as a side gig, as a butcher. So he would bring in beef hearts and other such things. And we spent a lot of time on meiosis and mitosis. If you didn't remember those, well, you should have had Mr. Foster. And we got another classic, kinky people can't order fried, greasy slop. Our physical sciences lab, the teacher's name escapes me, was also pretty solid. We did the classic acid and sugar to make a nice carbon block that would kind of grow out of the solution. And a few other things. This is, basic performative chemistry. So a lot of visual results, or a smell, or a color change. So the better living through chemistry observation, I suppose. These are the sorts of lab exercises that are interesting on their own, and our bio labs, when we had them, biology, were pretty educational. That was with Mr. Foster. But junior high school is preparation for high school when you really get down to it, and this was no more true than with the laboratory curriculum. So it was enough to whet the appetite, especially those beef hearts, but not. It was pretty much boilerplate labs, except for the fact that Mr. Foster would bring in extra stuff. It was pretty much probably pretty standard, probably an experience that most people had in any given junior high school anywhere. By the way, if you're curious, Kinky People Can't Order Fried Greasy Slop is a memory device for kingdom, phylum, class, order, family, genus, species, the animal kingdom. I guess the animal kingdom in that case does include flora. So it's animal kingdom is sort of, anyway. The high school biology lab. So our first year at Sunny Slope High School was reasonably boring. My science teacher, Miss Boris, was not so hands-on with the labs. We had a couple, but for the most part, this was an intro to physical sciences class again. So kind of a repeat of junior high school, sort of. I don't know if that's going to be a trend. I mean, as I was writing this, I was sort of thinking, until you pick your major, or until you actually begin to pursue your focus or your concentration, sometimes they'll call it, this kind of stuff is really repeated over and over again, for better or worse. So like everybody probably has a memory of a frog dissection or vivisection. So that's like a standard thing. And you probably did it at least once, but you may have done it twice. And if you went on to college and did any biological sciences, and if there was a lab class, you probably dissected another animal. Maybe it was a frog again, or we happen to have fetal pigs, which I'll get to in a second. So yeah, a lot of this stuff is repetitive. Maybe that's how we learn. I don't know. So the second year, bring on the biology again. Right? So we had biology, junior high, now high school. This time it was Mr. Breeze, Mr. Kim Breeze, if you're curious, who would at some point the next year attempt to shoplift from Smitty's, but he was captured. So that made some gossip news around the campus and whatnot. I don't know what was up with Smitty's and biology teachers. I think I've mentioned this, but I probably could have pursued bio research and life sciences or something like that. Maybe even could have been a doctor, but I was just not that into chemistry, as luck would have it. And I also didn't really like the sight of blood. That made doctoring tricky. Mr. Breeze was my biggest fan, and I pretty much aced the class. And then he went on to commit crimes, petty crimes. But my uncle was pre-med and had loaned me his vivisection kit with a couple of nice scalpels and some other useful tools for diving into our deceased laboratory animals. When we reached the fetal pig lab, I was able to remove the brain completely intact, which got me the big bonus points. I don't know if it exists anywhere on the planet anymore, but there was a jar of formalin with the fetal pig brain in it with my name on it. Yay! My uncle is dead, unfortunately, so maybe there is a family curse on life sciences. Engineering was the better choice. And I think that's been pretty much true. But knowing the endoplasmic reticulum, the loop of Henle, the phases of mitosis, all this stuff that's back from Mr. Foster's days. It's handy to know that stuff. It's nice to have some familiarity, especially if a global pandemic hits, to at least know where to begin. I'm not saying we're going to have a global pandemic. I mean, that would be crazy. High school physics. So year 3 in high school, the infamous Jack Trudeau, long since left the planet onto another quantum reality, perhaps. He, perhaps, one of the best teachers I've ever had, in fact. Jack, Zeke Ashley, I've mentioned him before. Maybe one or two others have really stood out. Those teachers that would probably get a 2-minute lifestyle segment on your local news or something. He was an overhead projector lecturer, not the chalkboard type. But he used color change inks in the pens, and he would swap out the next blank transparency to continue his lecture as the colors were changing. So it was one of those like, wait, were those colors changing? Like you had to really be paying attention and then note that between the beginning of the blank transparency and then when he was about to switch it, wait, that wasn't that blue? No, it's purple. Wait, what? Keeping us on our toes. It was a mysterious thing for a few weeks, but then we finally made a concerted effort. Like, okay, was that blue and now it's purple, or now it's pink and now it's orange, whatever it was. So good times. JT we used to call him JT, had a friendly feud going with our English teacher. Apparently one taught the other decades ago. It was never really clear which was which. In one instance of this pranking environment, we were to go through a ballistics lab, not firearms, but just the ballistic path of a projectile, where we would calculate the trajectory of a ball bearing, think pinball, right, a little bit smaller, as it was launched by a compressed air launcher, basically a pipe with a compressed air pocket at the back end, and it would fire the ball bearing projectile. So to call it a gun would be that's being generous, but so it would fire the projectile, the ball bearing, and the idea was to have the ball bearing hit a can that was hanging from a magnet several feet away. I think it was several feet, it was some distance. I think it was probably something on the order of 5 feet away from the end of the launcher, such that when the can would fall as the bearing left the launcher with a little trigger at the end of the barrel. So once it broke, I think it was I don't know, it must have been a light beam, because you couldn't interrupt the travel with a physical trigger. So probably broke a light beam, turned off the magnet, and the can would begin to fall. So the object was to demonstrate and to do the math. So you would prove through experiment the model of the notion that if you fire a bullet from a firearm, and you drop the slug, so one slug will come out the end of a barrel and it will fly through the air. And if you drop one from the same height, and they're both level, and so you're not giving it a angle, right? You're level with the Earth's surface. Yeah, I know it's round, unless you think it's flat. So when you fire and when you drop, the two will hit the ground at the same time. So you're demonstrating the two different components of ballistic travel, right? So the can weighed as much as the ball bearing, and the idea was to demonstrate this and then do some math to determine where it would hit and so on. So that was fun. But it was really like that. This was an extra element of the day. So when it left the launcher, the idea was to hit the can, and the real idea was to hit the image of our English teacher on the side of the can. And we hit him. We hit him right squarely. There was another version of this lab that was a little bit more practical, where we had to roll the bearing. We each had one of these ball bearings. We had to roll a bearing off of a table, lab bench top, through two ring stands. So you had to have the ring stands. If you don't know what that is, it's basically a ring of metal on a vertical stand, so you can adjust the height of the ring. The ring is parallel with the ground, and you can adjust the height on the vertical bar. So it's it's like a shower handle on a vertical bar that you can adjust the height. So we had two ring stands. We had to adjust their placement and height so that it would pass through both ring stands before it would hit a target on the floor, hard floor. And then there was a sheet of carbon paper over the target. And if you actually looked, which we did, of course, I mean, it wasn't secret, but yeah, so you're covering it with the carbon paper. But the reason to do that is because you wanted to capture where the ball bearing struck the target for the purposes of scoring. And the bullseye on the target, think darts, right? The bullseye on the target was indeed a picture of the English teacher. So good times. It was always, it was kind of funny because they were both actually friends. So, and we got him, and we got him on the forehead, which was fun. So the math worked out. Science wins again. Now, I was the only person in my physics class who had already taken calculus in the first AP calculus class at that school, taught by Geraldine Garrity. In fact, if you remember my episode about Zeke Ashley at Royal Palm Junior High, that's where Mr. Foster was and so on. I had a class of people. I mean, the people in my class were 1 year older than me. And so when I was taking calculus as a sophomore, the first time calculus was offered at the high school, all of my classmates were from Zeke's class. So memories. So I had taken calculus sophomore year, and then junior year of my time at Sunny Slope High School was the time for physics. It was interesting to be able to apply some of the stuff, right? So we learned about differential and integral calculus and F equals ma. Oh, that's just an integral. I mean, a differential. It's a derivative of a position function, all that stuff, velocity, position, right? So learning how that stuff worked and then demonstrating it. So physical experimentation with mechanics, physics, mechanics, parts of physics was interesting. And I think the take home from myself is that practical learning of some concepts is better for me than merely doing the math, as they say. Seeing it in action, feeling it in action is helpful for me to cement the notion, I suppose. But yeah, understanding where F equals ma comes from and then putting it to use in things like that ballistics lab were useful. So I think that's probably one reason I appreciate lab classes in school, is that it is part of a very useful learning process. Though in reality, most people do not take a calculus class in high school, certainly not early, sophomore year, second year. And very few people recall or would even think to look for a ballistics equation or how momentum works and so on. P equals mv, by the way. This is unfortunate. If you've ever cut in front of a bus approaching a red light and you've heard it trying to stop with the engine braking, and the whole bus does a little plowing because it's trying to stop because you cut its stopping distance, you forgot how P equals mv works. The bus has a much bigger M than you. High school chemistry. And one of those rare occasions where this is a good thing, we had JT for chemistry as well. Same classroom even. Jack of all trades, literally. So yeah, same room, same benches, same everything. Different approaches to learning. Everybody knows chemistry is just applied physics anyway. Or is it that physics is applied chemistry? I think Mr. Trudeau preferred teaching chemistry. He did wear a lab coat all the time, as you would in a chemistry lab, to prevent chemical spills from injuring you or ruining your clothing and so on. So yeah, he always had his lab coat on. Physics was not so wet. Where physics is practical when it comes to like driving, like not cutting off that bus, chemistry is really practical for things like mixing household chemicals that should not be mixed. Why gasoline will extinguish a match thrown into a bucket of it, but will ignite as it passes through sufficient vapors. Yeah. So if you dump gasoline on a burning match, it won't ignite. But if you, anyway, let's not even talk about it. Exothermic versus endothermic, enthalpy, acid-base titration, the whole nine. Here again, it is a real shame that most people do not really capture their high school chemistry lab experiences, especially how to apply them to real life. And honestly, if there was a cohesion in a curriculum arrangement, there could be a home economics class at the same time. So like driver's ed should be taught with physics, and home ec could be taught with chemistry. So you would indeed understand like what's going on if I mix baking soda with what is it when you mix baking soda with vinegar, right? What's going on with that? Well, here's the chemistry. So nobody asked me though. The really interesting part though was that the physics labs were interesting if he was setting them up and we were coming into the classroom. So he would be in the midst of tinkering with, for example, getting that can sorted with the magnet and everything. So as we're walking in, the magnet and the can was suspended by the magnet. So as we walked in the door, the can was kind of up to the left, and then the launcher was pointed at it on our right. So we're basically walking through the path of the ball bearing. So that gets your attention. Like, oh, what's this? So he was fond of doing that. But he would often have a chemistry surprise, which was very different and more spectacular at some point during the class. My all-time favorite, and he would have double clock experiments, so things would change color twice because the reaction would take a certain amount of time, clock reactions. He would demonstrate heat and enthalpy. He had here's a styrofoam cup. Should this be hot or cold? If you have a glowing red iron sphere that you dunk into it, or volatility, all kinds of things that were very practical and visual, or sometimes audio. So the all-time favorite, and this is a classic you can find in any chemistry lab cookbook, like, hey, if you're going to teach a chemistry class, you got to have these magic tricks ready. You fill a 1-gallon paint can through a hole in the side toward the bottom. If you're in a proper chemistry lab, you're going to have a gas jet somewhere near the sink. So probably methane. I don't think they would have allowed propane in a high school classroom. So methane, you want to fill that paint can with methane. We're off to a scary start, right? So you fill the paint can and then light the gas leaking out through a small hole in the middle of the lid. So that's at the top, and let it burn like a big candle. So during the lecture, the flame is getting smaller and smaller as the pressure of the gas inside is approaching atmospheric, right? So you're burning away gas. And at some point, the flame will drop down into the can and it blows the lid off. So it's a nice little noise maker. The can flies up into the air and bounces on the floor and makes a bunch of noise, and everybody's startled. What's going on there? And I will add, whenever something like that happened, because he's expecting it. So Mr. Trudeau's reaction to anything that was surprising or unexpected, but even he pretty much knew. Very, very little was unexpected for him because he was on top of the whole lab experience for both physics and chemistry. But he would do, this was his expression, ooh, that's it, ooh. And then like, did you hear that? Something like that. So definitely memorable. And this is a fine example where the teacher can make all the difference. He was off to college eventually. College labs are like high school labs, I have to be honest, because you're just getting started, right? They don't know for sure who had which kinds of labs and so on. So I was always going to pursue engineering. By the time I reached Harvey Mudd, I mentioned an interest in bio. I was interested in all the pure sciences, but during the biology lab, there was a part where we had to take our own blood sample to do blood typing as one of the labs. Now, the lesson I learned was that you don't need to poke the end of your finger where the nerves are. You can poke the side of your finger where there's almost no nerves. It works just fine. Over the years, I have come to learn this, and if I'm doing a keto serum measurement, I can take a drop of blood from the side of my finger. It's almost painless. And there you go. But in my biology lab in high school, the thought of poking myself in the finger to get blood out was like, I don't want to do that. And I was actually feeling like lightheaded and dizzy and so on. So yeah, I was not a fan. So yeah, that would have been a bad look for a doctor who doesn't like the sight of blood. I think it was more my blood than someone else's blood. Anyway, so on to eat, and I did the fetal pig, right? And that was not a blood-free process. But again, not my own blood. So who knows how the world would have worked out. But I was going to be an engineer, whether I was doing it in an airplane or not. So my main pure sciences labs were during the first year of college. We took chemistry and physics, the usual first year curriculum. Basically, introduction to these topics from high school. Most of the students had a reasonable high school background, so pretty much some lab experience, the basics of both of these sciences. So aside from the fact that we were working with slightly more dangerous chemicals and lab equipment, it wasn't such a big deviation from high school labs. Like we were allowed to heat things up directly into, here, this is a base, be very careful with this, not, you're only a high school student, you're not allowed to touch this, that kind of thing. To give you some idea, one of our chemistry labs was using a Gooch crucible to vacuum filter a solute out of a solution and then weigh the solute to determine some properties of the original solution. It's basic chemical handling and chemistry lab processes and techniques. The Gooch crucible is it looks like a little shot glass, borosilicate, of course, with a hole in the bottom, as in most of the bottom was missing. So the flat bottom was a complete circular entry, just like the top of the Gooch crucible. So kind of a tube. It was tapered. And then there was not porcelain, but there was a porous material that looked like porcelain between the upper part of the Gooch crucible and the bottom. So you can look this up. I think I've spelled it correctly. It's Gooch. So with the Gooch crucible, you could use it to vacuum filter things. Let me look this up real quick. Gooch crucible. Yep. The pictured ones are more ceramic looking. There's glass ones too. So anyway, borosilicate. So you would have a vacuum hose, because our chemistry lab now had gas, compressed air, and vacuum, right? So you could just vacuum. Who knows where those vacuum tubes were going to, but so we hooked up a vacuum hose to a vacuum, kind of a funnel looking thing. So on the side, there's a little attachment, stick the hose on there, and you put it into like a flask so that anything that would come through, any liquids would land in the flask. So you generate this vacuum from the vacuum tube, and that would draw air through the top of the Gooch crucible, through the porous material, and then land in the beaker. So the effect is vacuum air drying your solute, but without the solute as the stuff dissolved in the solution, but without sucking it up into the vacuum, right? So if you're trying to get a vacuum filter liquid to get a solid out, and the solid is powdery, if you just vacuum from the top, the powder is going to go up into the vacuum and experiment over. So it's pretty cool device. This is the sort of thing that you learn in a class like this, because that's the introduction to your chemistry focus if you're focusing on your concentration. So if you're a chem major, you'll be doing a lot of this kind of stuff. For us, it was like, oh, that was kind of cool. I happened to be looking through the window that separated, our lab was two physically different rooms with a big giant, like heavy duty window between. I think I talked about this when we had the earthquake. A classmate of mine, Kevin Cornet, thought it would be a good idea to blow into the top of the crucible after it was filtered. So I happened to be looking at him as he removed the crucible from the glass funnel. So it was done vacuum filtering. And he looked into the crucible and then he blew on it as though, I think you can imagine kind of a quick, I don't know if that'll make it through the silence truncation, but either way, I think it will. A nice quick blow for whatever reason. I don't know what he was thinking, but it left his mouth and chin covered with the solute powder, whatever it was. I think it was a little bit yellowish. So very obviously not a powdered donut. And I saw the whole thing. Kevin Cornet would die several years later from a congenital heart defect. It's unfortunate. He was an interesting person. Very nice guy. Physics labs were basically mechanics. So an air track to work through conservation of momentum, things like this. The chem lab was more fun and interesting, I have to be honest. I guess that's just the way. Chemistry lab is just more chemistry. I believe I mentioned this in a previous episode. It was during the second semester of our first year in the chem lab. I had just turned around to lean on our lab bench while my lab partner, different Kevin, went to ask a question of our lab professor. I think she was the department head at the time, Dr. Carrie Caruxtis. And the Mount Baldy quake commenced. Various stories and recollections concerning explosions and chaos were a bit much. I think one water pipe cracked with some water shooting into the lab space and some glassware fell off lab benches and stuff. So not too bad, but it was certainly a memory to be in an earthquake in a chemistry lab. Good times. And then there were, there was the sophomore year, second year of college. This was a real departure from the high school sciences. We were definitely not in Kansas anymore with electromagnetism and optics labs on the physics side in the first semester, and in the second semester, experimental engineering. Now, E&M lab, as we called it, which doesn't make sense because it's electromagnetism and optics, so E and O. But E&M lab was interesting and a bit practical. My favorite was actually deriving some RCL behaviors through experiment. So going through the model, that is a resistor, capacitor, inductor, RCL. Well, yes, inductor is L. A resistor, capacitor, inductor circuit that is an electrical analog to a driven damped harmonic oscillator. And we convinced ourselves of that right there, because the model for a spring damper system, your car has 4 of them. Driven damped harmonic oscillator is basically some driving force, like the ground pushing up into your car, the mass of the car, the spring damper, that is the spring, the coil springs and the shock absorbers, and the motion of the car, and how you can tune different parameters to make the ride smoother. Well, there's an analog for that in electrical systems for the RCL circuit. They behave almost exactly the same way. In fact, mathematically, the same way. And it turns out that RCL circuitry appear pretty much throughout any sort of design of speakers, for crossovers, the speaker drivers themselves, and so on, if there's any other electronics involved. But loudspeakers are basically RCL science experiments. And so I had built my own speakers and I designed my own crossovers by this point. So it was sort of a practical hands-on example once again. And it was like sort of like viewing all this from a pure science perspective. Oh, this is how speakers really work from a physics perspective. So that was pretty cool. And then there was E54, experimental engineering. This was in a league all its own. And they no longer teach at Harvey Mudd College. It was retired several years after we were there. Now they teach a class called E82, which includes rocketry, I guess. And I don't think, they reduced the number of tools. E54 had an entire metal and wood shop and sheet metal shop component that I believe they've cut down the requirement. Maybe it was just too much for these kids, but it was a lab class, but just the lab class. The shop class was a different thing, in which we also received no formal training in. So that was kind of fun. So a lab class beginning in the evening for part 1. So I was in Monday group 1. So Monday night, we would go down after dinner to the lab and start working on the labs. And then the lab would end. I think it was 4 hours. I had to be maybe 3 hours, maybe 6 to 9 or something like this, PM. And then we would leave. It would return the following afternoon. And so part 2 finished up in the afternoon. Then we were done. We would turn in our lab notebook for the week, whatever we had finished. But we could not take the lab materials. We couldn't take our lab notebook or anything out of the lab before we returned the next day. So any sort of discussion or research that we would do, or any pondering had to be done from memory. And with the bonus indeed, probably the best part of the whole thing, the lectures that were appropriate. Now, so in chemistry lab, most of your chemistry laboratory experience is going to be connected in some way with the lectures that you've been having. And indeed, because they're sort of introductory and a throwback to high school chemistry, you're not going to encounter things that are completely outlandish, right? Not so the engineering department of Harvey Mudd. So we didn't have lectures about the topics in the laboratory until after the laboratory itself. For example, we were supposed to design an elastomer, so a rubber shock absorber, an elastomer to dampen our fictitious CD player from base excitation. So an input from the ground, right? So you're walking on the floor of your home, and you're injecting oscillations into the furniture that goes up through wherever you're resting your CD player. So you want the CD player to remain stationary so it doesn't bounce and you don't get skipping. So we had to design an elastomer. Well, we had not taken any of the classes necessary to learn how to model the response of an elastomer to base excitation. We did have some rudimentary materials that we had kind of learned about for a top excitation system, but base excitation makes a small difference because of the direction of gravity. And there were some other things about the material itself and the material selection process and everything. So these were all new things. So all of the lab modules or assignments were like this. We had to design a sprinkler system, which was critical to understand pressure drops across bends and lengths of tubing pipes for your sprinkler system. So we had little pressure sensors on either end of different segments of a kind of a U-shaped loop. So we should have been able to determine what these drops were, but we really didn't even know what we were getting ourselves into. And as luck would have it, the three of us in my lab team, it was myself, it was Kevin Cornet, remember Kevin, and super nice guy, and a student named Terry Wooldridge. Terry was in my freshman orientation group of like 5 or 6 of us. So Terry began the first day of the first lab where we got our team assignments. Oh, it would have been too nice to be able to pick our own teams. It probably would have been me, Kevin, and Tuck, my roommates. But the three of us were in the same lab, but we were in different groups, different teams. So Monday, group 1 meant that our team of 3 was the first team to do a lab, any given lab, on Monday. So no one else had done any of the labs since the year before. And no one else, because everyone in the room was working on a different lab, right? Every single person, every team was sitting at a bench for a different type of lab. So there was really no one to collaborate with or ask, is this what you got? That kind of thing. So it was a challenging time. So Terry is an athletics person. He's like, I don't want to do this because I'm going to change schools. Okay, great. And then Kevin Cornet, the third in the team, Kevin said, I'm really good at writing up labs. So he was going to concentrate on taking data and writing it up. So guess who had to try to figure out what the hell was going on all the time? Right. So that was fun. It was definitely educational. And here's the fun fact that they don't tell you. And if you are going to Mudd right now, it doesn't matter. They don't have the class anymore. We were Monday group 1, right? Lab, I think what was it? Day 1, group 1 or something like this. So they didn't grade on your results. They graded on the fact that you did the work and that you made a good attempt, because it turns out they understood completely that they didn't teach us anything ahead of time. This was purely learning how to learn on the fly. One of the labs was a torsional pendulum, and you had to model it was a paint can again. Paint cans make a lot of appearances in these things. So a paint can with an adjustable weight hanging from the bottom, and a metal rod, steel rod, that it was suspended from. So the paint can could rotate along the axis of the metal rod, so torsional pendulum, and you wanted to determine a period, so a rotation like a pendulum, right? Torsional pendulum. So how long would it take to go from one end of the rotation to the other, right, and back? So you wanted to adjust that, and you could adjust the mass with the weights on the bottom of the paint can, like hanging from the bottom, rigidly, so they didn't add to the rotational components. That is to say, they rotated as a single mass. And you could add a dampening fluid in the form of antifreeze. So antifreeze is a viscous fluid. So you could adjust the viscosity of the fluid and the amount that you would put in the paint can and determine how to best design this torsional pendulum with dampening. So later we would learn that it was not actually possible to do that. That the math was hard enough, and we hadn't had the math for that, differential equations. And we did do differential equations, but this was very advanced stuff. And at the end of the day, it was a really complicated system, so not really possible to solve. But the effort was what was graded. So we ended up getting a really good score, probably an A or an A plus, because we were Monday Group 1, Team 1, Group 1, whatever. And they took that into account. Like, oh, this is the team with the worst possible initial conditions, right? They can't ask any questions. It's the toughest group to be in. So yeah, for all of our stressing over it, we did fine. So that was very educational. The rest of my college career, all of our labs were based on specific projects. Take a deep breath. Our sophomore year, our junior year, our sophomore year was those two were the big lab classes. I never took a biology lab class. Biology had just become like a new addition to the core curriculum. So it was classroom only. That probably would have been interesting. Our what was it? Pervez and Mueller? I think it was Mueller. Really, really good team of teachers teaching the first year biology class. Anyway, so no lab class. They were really big on nerves, like action potentials and clamping and so on. So that probably would have been interesting. So we did our 2 years, and then by the time you're junior and senior, you're in your concentration. So I'm actually second semester. So not everyone took experimental engineering lab. Everyone did take E&M lab. So E54 now behind us. We're all engineers. We're doing our various projects and so on. So I was in a project to do a programmable radio receiver, the digital receiver DR01 from ESL, a division of TRW, blah, blah, blah. So we built a computer interface card, a new bus card that would go into a Macintosh 2FX. And we learned LabVIEW, and we built this whole demonstration system that was very modular. You could program it visually with LabVIEW, and you could capture radio signal data and had rotating phasers that you could shift the incoming signal and so on. So all kinds of fun stuff. So that was a laboratory, but it was hands-on to develop the particular project we were working on. So all the stuff we had learned from lab practices and hands-on, like figuring out if things worked, was great. This was an electronics application, so there was really no liquids and biological hazards to deal with. The second year, we were to design a filter system or something that would enable a laser that was being sent out the front of the sensor called the OASIS, the obstacle avoidance system, was to be mounted on helicopters. It was to point forward, and it was to pierce any aerosols in the air like smoke from a fire, and the laser beam would return, and depending on when the returns arrived, you could determine. So there's LiDAR today. That's pretty much everybody uses LiDAR in self-driving cars except for Tesla. So LiDAR can be used to scan a region in front, and the laser beam returns will give you a representation of the terrain ahead, right? So here, the OASIS system was supposed to design in real time a safe flight path in case there were obstacles like mountain, surface, or power lines, electrical power lines. Laser returns off of high tension cables are very tricky. So I don't know if that ever worked for version 1. It kind of worked, like you would pick up the poles or any infrastructure that was holding up cables, but the cables themselves were a little bit tricky. The laser returns off of a cable there's a lot of loss, right? So you don't get much of a signal return. But anyway, we were to design some way of preventing the return sensor from saturating, because whenever you would turn on the laser, because of the physical design of the system. When the laser came on, various reflections within the system would cause the sensor to saturate. So the sensor had to turn off and turn back on in sync. It was almost like a propeller machine gun gear so that you could fire back in World War I. Remember that? You could fire the machine gun between the propeller blades, right? So it was the same idea. So that was fun. Did we have another? I was a lab assistant for E54, and there was probably some other stuff. And of course, in the real world, you do a lot of practical hands-on things. Depending on what you actually do, you do these things at home. Like I mentioned, home economics and chemistry probably should be taught together. Don't mix that with that other thing. So don't put that sodium metal in the water. Why not? Well, you'll find out. So that's the deal. I think laboratory classes, and this is where I'm kind of a fan of the flipped classroom in general. So all of education could really be thought of as laboratory classes, like practical application and discussion. Everything we did in the chemistry lab, we could read about ahead of time or take a lecture and so on. So when you can separate them, that works out nicely. In a flipped classroom scenario, basically you're saying, oh, okay, so in high school or maybe elementary school, students are essentially they're in the same classroom setting, usually for the first 6 years or so, five or 6 years. Then junior high school, maybe you're switching classes and so on. But you're essentially, you're still fixed to the normal school day, and you can't really ask much of students to go home and do 12 hours of homework. That's not going to fly. College, they're happy to do that. But you can't really have especially by the time you're in high school, maybe you have a school job, after school job and so on. So it's tricky, but if it's possible to somehow manage a practical part of a classroom experience and then leave the learning to outside of classroom discussions or self-guided reading and so on, I think you end up with a better educational outcome overall. But that's really hard to convince people to experiment with. So finding a flipped classroom school or flipped classroom curriculum implemented at a school, probably something of a challenge. But who knows? It's something I've talked about in the context of the Innovate for Vegas Foundation. If we do ever pursue our education Apex initiative, so it will be made up of various other initiatives. Mostly that would be a question of how you learn from the students about how they would like to learn, or maybe how they might learn better, and who better to ask than the students, assuming they're honest. But anyway, that's a whole other story for another time. I'll leave it there. I could probably talk more. Like I said, I could do an entire episode about each E54 class. The RCL lab, I'm sorry, the PID lab, not RCL. The PID lab, probably the most practical of any of them. I'm not going to design a sprinkler system so often, or I'm not going to do elastomer design. I'm not going to do metal failures. So I don't, Young's modulus doesn't come up in conversation much. But PID control, proportional integral derivative, or sometimes PI or PD, these come up every single day whenever you adjust your thermostat. If you have some sort of central heating or cooling, whenever you adjust the temperature on your oven, if you still use one of those, if you have an automatic kettle, as I do, and you set the set point temperature, it's using a PD controller. So those will have steady state error, but proportional derivative. So you basically say, I want to get to 100 degrees Celsius or 212 degrees Fahrenheit. Well, that's easy. You just turn off the heating element when it reaches the maximum temperature, because you can't really go over that. Not in your normal kitchen. So suppose you want to heat water to 200 degrees, or for example, my yerba mate, I usually go to 75 degrees Celsius. And for coffee, for a dark roast, I'll go to like 85, 83, 85, somewhere in there. So here you want to say, okay, at any given time, we're at 65 degrees, so we have 10 more degrees for tea or whatever. So what's the absolute difference between the P and the D? That's the proportional band. So we want to say, okay, so the proportion of control that we want to do it's in direct proportion to that difference. That's called the error signal. So the difference between where we want to be temperature-wise and where we are, called the error. So the proportional difference the proportional relationship between the current and destination or target temperature, we can adjust with a proportional value. So we'll say, oh, it's the difference will multiply by 2 or will multiply by negative 0.5 or something. And then we take the differential, which is how fast the temperature is rising. So if the temperature is rising really quickly, we must have a really high input or high output heater that's inputting heat to the system very quickly. So the temperature will be changing very quickly. So the differential element will be reflected, or it will reflect that high energy input, right? So the temperature is going to change very quickly. We're going to be far away from the set point, then we'll get closer and closer. And the rate that we're getting closer can also be a term. And then the integral, if there is an integral term in the controller, integrates the error over time, and that will help prevent steady state errors. So my kettle, I've found, will pretty much reach the set point temperature, but then it will overshoot. So if I set it to 75 and then if I pour out some water and I put it back on the stand there, it will heat up to 77. If there was an integral controller, they would integrate that 2-degree error over time, and it would drive it in the opposite direction. So the temperature itself is no longer changing if it's sitting at 77. So the differential term will go away. And if you're in the proportional band, you won't have any proportional control. So the error will just sit there. It'll sit at 77 until it just cools off on its own. My kettle has no cooling element, but if there wasn't, so that's why integral control doesn't really make sense. But if you had an integral term, you would take that error and you would say, oh, okay, so we're 2 degrees over. Let's either remove some heat through a cooling element, or we'll vent some heat, or we'll add some more cooler water, room temperature water. So anyway, all this stuff, totally interesting. So the PID control lab, the most fascinating. And we were actually, the goal is to design the control parameters, PID controller parameters, to account for what's called a Poisson delay. So there's a delay in the sensor reading because the heat has to go across this rod that we were measuring the temperature of. And there's transient error at the beginning. Right. So what's going on? We don't know. We don't have real error. So Poisson estimation of that delay. And then that delay would be pervasive. So anytime you're adjusting the temperature, there'd be a delay between the time that you change the settings. So you're heating one end of a rod. I didn't mention that part. You're heating one end of a rod and you're measuring the temperature at the other end. So there's the delay involved in getting the temperature to change from the heating end to the measurement end. So all kinds of stuff. If your thermostat is in one part of your house, but the other end of your house is always hot, something to think about. All right, I'm going to leave that there. Thank you so much for listening. As always, don't forget quaglingsand.com. At some point it will look nicer, but I'm taking ownership of all of my brands, so you should always be able to find not only that show, but if you don't want to go to buymeacoffee.com/DanHugo, I will cross-link all of my stuff too. So that's where we're going to leave it for today. Thank you so much. And go do some lab classes, like throw an egg in the microwave and see what happens. Take care. Bye-bye.